Okay, good morning, everyone. So today we are going to be talking about almost degenerate perturbation theory. Which I'll abbreviate as PT, since we've been talking about perturbation theory for a while. And so here's the idea, is we have some Hamiltonian, which as usual, we divide into an H0 part and a W part. And we're asking the question, what happens if, when we look at the energy differences, which we've been calling epsilon nm. All right, so those are the differences in unperturbed energies of H0. What happens if those are much, much less than the perturbation theory matrix elements, WMN, which is our notation for the matrix element MWN? Okay, and I guess I should really put absolute values around the energy differences because they could be plus or minus, but we're really asking about what happens when their magnitude is much smaller than the perturbation. So intuitively, that means we don't really have any business treating the perturbation as a perturbation. It's not small compared to the energy differences that we're talking about. Okay, and indeed, that's a problem because when you go to higher order in lambda, and I guess if I'm talking about lambda, I should really have restored my lambda here, which we often set to 1 later. But higher order in lambda means higher powers in lambda, which will mean more powers of the energy differences in the denominators. And so if they're relatively small, then the terms will be getting bigger and bigger, not smaller and smaller, and so there will be no convergence of the series. Okay, so that's the problem that we have to solve with almost degenerate perturbation theory. And so by way of motivation for how we're going to solve it, first let's rewrite our W thing that we're trying to treat as a perturbation. What we're going to end up doing is not treat it as a perturbation after all, but do something cleverer. So if we write W, we can do completeness twice. And so let me sum over states N and sum over states M. And I'm putting in the identity operator twice here, one on either side of W. And among all the states that we're summing over, suppose there's some subset that's almost degenerate. So I'm going to denote that subset of states that are almost degenerate by giving them an extra subscript, K. Okay, and so suppose that subset have very close energies, curly E sub N sub K. These are the almost degenerate states. Okay, so now the idea is if we stare at our expression for W, we could say, what happens if we change W to only sum over the degenerate states instead of all the states? So what we're going to do is we're going to define a sort of a new version of W where we do that by sandwiching on either side of it a projection operator, which I'll write down what it is in a moment. But basically, the projection operator here is supposed to project you only onto the almost degenerate states. Okay, so P degenerate is defined to be, instead of summing over all n's, we just sum over the n sub k's. So any operator of that form is a projection operator. And so in words, what we've done is we've defined W degenerate to be the operator W, but confined to or restricted to only the subspace of almost degenerate states. Okay, so now the idea is to redivide our Hamiltonian into a different perturbed, or unperturbed and perturbed part. Okay, so now we're going to redivide Hamiltonian into what we're going to call H0 prime plus W prime. And so H0 prime is going to be the old H0, but we're going to add in the W degenerate part. And then we're going to compensate for that by taking the old W and subtracting it off. So we've done nothing. We've just added and subtracted it to different parts of the Hamiltonian. But now H0 prime is going to be our new thing that we have to solve exactly. And we have to assume that we can do that we can solve it exactly. And the W prime is our new perturbation. So we treat this as the perturbation. And note that it's equal to 0 for all the almost degenerate states. And the reason it's equal to 0 for them is because basically we subtracted out here the part that is non-zero for the almost degenerate states. Okay, so there's a nice principle of solving problems that if you can't solve a problem, you should just change the problem. And so that's what we're doing. We're redefining what our perturbation is and what our unperturbed states are. So why is this going to work? It's going to work because now we've constructed a perturbation theory where the bad denominators won't be there. So bad denominators, meaning small denominators, are going to be absent because, by the way we constructed it, all matrix elements M sub k, W prime, N sub k are just 0. So this is true within, I should put in parentheses, within the almost degenerate subspace. So now if we do what we've been doing with ordinary perturbation theory, but with this revised problem, we won't see any of the bad denominators just because any of the matrix elements that would try to connect states with very small denominators are just absent. They're just not there because of this selection rule. Okay, so let's do this by doing the simplest, actually the second simplest possible example. And then after we do the second simplest possible example, we'll come back and do the simplest possible example and see why it's too simple. Okay, so the simplest possible example is this. It's actually going to be a 3-state system. So we'll call our states 1, 2, and 3 because we don't have much imagination. Okay, and then within that basis, we can construct the Hamiltonian just by telling you what its matrix representation is. And so we'll take the matrix representation of our H0 to be this. So I'm going to make it diagonal. And on the diagonal, I'm going to call it A minus delta, A plus delta, and B. And the delta is supposed to be small. So in the limit where delta is very small, then the two eigenvalues A minus delta and A plus delta are almost degenerate. Okay, and then I put zeros everywhere else. Okay, and then our perturbation is going to be off diagonal. The perturbation doesn't have to be off diagonal. I'm just choosing it to be off diagonal for this example. And it's also going to contain some small numbers, which I'm going to call delta and epsilon. And I'm just going to put them where I've shown them there, with zeros in the bottom right 2x2 submatrix. Okay, and so we're assuming that A and B are nice large numbers and they're not too close to each other, but capital delta, little delta, and epsilon are all small. Okay, and the fact that capital delta is small is what's telling us this is almost degenerate perturbation theory, or that we're going to need almost degenerate perturbation theory. If little delta and little epsilon were small, that's no problem, because that's part of the perturbation Hamiltonian here, and you want that to be small. But this is the problem, that these are small. Okay? So to see what goes wrong, let's first try to do this using ordinary perturbation theory, and we'll see what happens. So first, try ordinary perturbation theory. Okay, and so first let's just write down our unperturbed energies. Those are just the eigenvalues of H0. So curly E1 is A minus delta, curly E2 is A plus delta, and curly E3 is B. We're just reading that off the diagonal. And now we just do what we're told to do in perturbation theory, which is we construct the energy at first order in perturbation theory for each one of our states n, where n is 1, 2, and 3. And I'm going to be doing these all at once. And the reason we're going to be doing them all at once is because they're all 0. Right? And how do we know they're all 0? It's because if we stare at our W here, our W has zeros on the diagonal, and the zeros on the diagonal are just these matrix elements, the expectation values of W. Okay? So at first order in perturbation theory, there's nothing to do, for the energy at least. And now for second order in perturbation theory, actually, let me do these one at a time because they're different now. So I'll do the energy for the first state at second order in perturbation theory. And remember, that's like a matrix element squared divided by energy difference summed over all the states. And so it turns out there's 2 terms here, because for any given state, there are 2 other states that you have to sum over. You never sum over the same state. So there's an epsilon squared divided by an energy difference, which is A minus B minus delta. And then there's a term from the delta matrix element squared. So that's delta squared over the energy difference, which is 2 delta. Right? And the 2 delta is coming from the difference between that unperturbed energy and that unperturbed energy right there. Okay, so that's our first correction, or second correction to the first energy. And then our second correction to the second energy is equal to, it turns out now there's only one term that's non-zero, and it's delta, little delta squared over 2 big delta. And then for epsilon 3, it's minus epsilon squared over A minus B minus delta. Okay, so now the problem is, well, first of all, for state 3, there actually isn't a problem. There's nothing wrong with this, because A and B are supposed to be nice and big and different from each other. And so the non-almost degenerate state doesn't have a problem. But for our 2 almost degenerate states, these terms are the problem. And they're the problem because delta, capital delta, could be very small. Okay, so these are bad. because the 1 over deltas are trying to tell you that you're not going to get convergence. And we won't do it, but let's say you did the kth order contribution to one of these states, you would find out that it goes like 1 over delta to the kth power. And so if delta is a small number, then this is not small. Okay, so that's really just illustrating the problem. Any questions so far, by the way? No? Okay. So now we're going to apply almost degenerate perturbation theory. Okay, and so we had a recipe up above for what we're supposed to do. The first thing we want to do is we want to construct the projection operator onto the almost degenerate states. Okay, so this is some operator, but I'm just going to write its matrix form. And so intuitively, what this thing is doing is it's projecting onto the first 2 states and projecting out of the 3rd state. And so to write it down, what you do is you just put the identity matrix for the 2x2 matrix there, and you put zeros everywhere else. Right? That projection operator projects you onto the first 2 states and throws away the 3rd state. Okay, and so if you apply that to W, the W degenerate is just going to be what you get by writing down the same thing for the first 2 states and then rejecting everything else. So you put zeros everywhere else. And so now from those, we can construct what H0 prime is. And so what that is basically I take this thing and I add it on to my original H0. So when we do that, we get A minus delta, little delta, A plus delta, and then 0, 0, 0, 0, B. So the idea is we're supposed to solve this exactly. So this is the sort of weakness or the difficulty in almost degenerate perturbation theory, is that sometimes you have to solve something exactly that might not be easy to solve. In this case, we're lucky because I chose the problem carefully. And so in this problem, it just so happens that we can solve this exactly because it separates into a 2x2 part, and any 2x2 matrix we can always solve, and then a 1x1 part, which is of course trivial. Okay, so that's the H0 prime that we're supposed to solve exactly. And then there's the W prime. And so there what we do is we just put whatever we didn't put from W into the H0 prime. And that turns out to be this stuff. Okay, so it's just the epsilon part. Okay, and this is our new perturbation. Okay, and so another way of writing this, by the way, you can always do all this stuff in Ket language rather than matrix language. And so if you were to want to do that, you could write this in the following way. This is going back to our original sort of motivation for how we defined the projection operator. So this is a way of writing the actual operator. This is really just the matrix representation for the operator. All right, so now let's go ahead and do this. The first thing we have to do is we have to do this part. We have to solve this exactly. And so let's just write down the result for that. Curly E1 prime is going to equal A minus square root of delta squared plus delta squared, capital delta squared. Curly E2 prime is going to be A plus that, square root. And curly E3 prime is the same thing as curly E3, so that's B. And then you have to do a little bit of 2 by 2 matrix diagonalization. So I'll just tell you what the answers are for that. So the state 1 prime, which is the eigenstate of H0 prime with eigenvalue, this eigenvalue. So that turns out to be this. It's square root of R plus over 2, 1 minus square root of R minus over 2 times 2. And for 2 prime, it's this. So I have to tell you what R plus and R minus are. And the hard part of this is really just normalizing these cats. So it turns out when you write this down, okay, R plus and minus are 1 plus or minus capital delta over square root of little delta squared plus capital delta squared. Okay, so you just have to diagonalize that 2 by 2 matrix and then normalize it, which is the not so pretty part. And then, which gives you these square roots. And then, fortunately, in this example, 3 prime is the same as the original eigenstate 3. Okay, so that's the unperturbed states, and now we have to do perturbation theory with those states and with H0 prime and W prime. And so what do you find? So first of all, you find, again, just like last time, that at first order in perturbation theory, let's say for the state E1 prime, you get 0 again. Okay, and that's just because W prime is off diagonal, just like W was. Okay, and whenever you have a perturbation that's off diagonal, that means diagonal, I can't spell today. Okay, and whenever something's off diagonal, then the expectation value is 0, and therefore the first order correction to the energy is 0. So then we have to do second order in perturbation theory. And in this example, there's only one term in the sum that contributes, and it's this one. Okay, and then you just have to plug in the results above. And so this turns out to be epsilon squared from the matrix element. And then from the other parts, there's R plus over 2 A minus B minus the square root of delta squared plus capital delta squared. Okay, and that's just for the state 1 prime. In the notes, you can find the results for the states E2 prime and E3 prime. I'll just write etc. here because I'm lazy about writing things out today. Okay, but so the idea is this is hopefully going to converge better. It will converge better if this denominator is not small. So I will write here, hopefully, because you notice there's no guarantee actually that it will be not small. It could be small if, let's say, A and B were actually closer together than we were hoping for. And so the question is then what do you have to do? Then that's a sign that you should have done almost degenerate perturbation theory on all 3 states together. But that's not really an advantage because what does almost degenerate perturbation tell you to do? It tells you to completely exactly diagonalize the Hamiltonian on all 3 states. And that's the exact same thing as the original problem. So almost degenerate perturbation theory isn't a magic thing that works in every situation in a beautiful way. There are some cases like if A and B were close together and delta was small, then all almost degenerate perturbation theory would tell you is solve the exact problem and good luck, right? So it's not helpful. Okay, but in many cases, it will be helpful. Okay, so et cetera means similarly for E2 prime and E3 prime. Okay, any questions on that example? All right, so if not, let's actually do the simplest possible example of almost degenerate perturbation theory, and that would be the case if you had a just 2x2 matrix. And one of the reasons I want to talk about that is because it illustrates an important qualitative concept called level repulsion. And so we will illustrate level repulsion, which applies in many situations, including very complicated ones. But the whole idea is just that perturbations tend to move energies apart rather than closer together. So if you have some system and you can solve it exactly, and you have some eigenvalues, and then you apply a perturbation theory, or you apply a perturbation, you should expect the eigenvalues to get repelled from each other. All right, so our very simple model for this, which is just going to be 2x2, is we have a H0, which is that. That's sort of already solved. And then we have a perturbation that's going to be off diagonal. We might as well choose it to be off diagonal because if it had a diagonal part, we could just absorb whatever is on the diagonals here into the corresponding H0. So why wouldn't we? Right? So it's natural to assume W is off diagonal. And if I wanted to be really general, I could make them complex here. But then it's got to be Hermitian because the Hamiltonian is an observable. And so if I choose my delta to be complex, then the off-diagonal elements should be complex conjugates of each other. Okay, but we're actually we'll just assume that delta is real and small. Okay, and we're also, well, A and B have to be real because they're on the diagonal to make this thing be Hermitian. And we're going to assume that B is greater than A, or at least greater than or equal to A. And that doesn't, that's very general too, because if it wasn't true, we should just interchange the two states and then it would be true. Okay, so we can assume B is larger than A. And in that case, before doing any perturbation theory, we can just write down the exact result by solving the eigenvalue problem. And the two exact eigenvalues that we can try to look for in perturbation theory are 1/2 times the sum of A plus B plus or minus the square root of their difference squared, but also under the square root is 4 delta squared. And so that's telling you why level repulsion happens. You're sort of splitting them apart, but then when you split them apart, you add something under the square root, and that makes the splitting larger than it would have been if delta were absent. So that's the basic idea behind level repulsion, except that you can apply to this to 7x7 matrices, and you find out that it's just a general property of eigenvalue computation. Okay, so now for this example, let's consider the three kinds of perturbation theory that we've talked about. So first of all, there's the non-degenerate case. So non-degenerate perturbation theory. If you apply that to this example, then you will find the eigenvalues are A minus a correction, which is delta squared over B minus A for the first one, and B plus delta squared over B minus A for the second one. Okay, and these are the second order in perturbation theory contributions. The first order in perturbation theory contributions vanish because the perturbation was assumed to be off diagonal. Right, and so it's a general fact that it's going to be quadratic in this case. And so if I graph as a function of delta, what are the energies? One of them is going to start off at A, the other one's going to start off at B. And then the lower one, notice we assumed that since we're assuming B is larger than A, this is a positive number in the denominator. This is a positive number in the numerator, and we're subtracting off something. So that means this is going to get lower. And for the state that started out at B, it's going to get larger. And so that's the quadratic level repulsion. You have to work to second order, but it's quadratic, going like the square of the perturbation. Now suppose instead that A was equal to B, then we should be doing degenerate perturbation theory. So this is for the case A equals B, and then that's a really easy 2x2 matrix to diagonalize and find the eigenvalues of. And actually the results are exact as A minus delta and A plus delta. So once again, the two energies are getting repelled from each other. They sort of had to be because they started out equal, right? And so they both start out in this case at A, and one of them just grows linearly and the other one just shrinks linearly. What else are they going to do when you perturb them? They're going to move apart, right? So this is first order, and notice it goes linear in the perturbation. So we saw this in action when we did the Stark effect. When we did the Stark effect for the n equals 2 states, those were the degenerate states, then we got the linear Stark effect where the energies got repelled linearly. When we did it for the n equals 1 state where it was non-degenerate, then we had to go to second order in perturbation theory, and then we got the quadratic Stark effect. For homework, you are going to get to do the Stark effect at the n equals 3 level, and that's once again going to be degenerate perturbation theory, which you should be happy about because degenerate perturbation theory is actually easier than non-degenerate. One of the reasons it's easier is because you are only doing first order to see the effect. If it had been at second order, then you'd be having to do a more complicated formula. So you got to do the n equals 3 Stark effect for homework. That's due a week from yesterday, I guess. Okay, but then the third case is almost degenerate perturbation theory. And there you're instructed, so that would be if A and B are very close together. And there the formalism tells you you're supposed to solve the exact problem. So for 2x2, there's no distinction between the exact problem and almost degenerate perturbation theory. Always. So this is same as exact. And so if we just make a sketch of what the formula, this formula up here, that's the exact result. We sketch what that looks like. Okay, as a function of delta. And now I'm taking as my starting initial condition, the two states are very close together. This is A and this is B. And if you graph it, you find out it starts out looking quadratic. So it's going up a little bit, and this one's going down a little bit. And then when delta gets larger, then it starts to go linear. So it asymptotically goes linear, sort of like that. Okay, so it's quadratic for small delta, which really means magnitude of delta much, much less than A minus B. And it's more like linear for delta much, much greater than A plus B. Okay, and so once again, we see the level repulsion principle in action, that the eigenvalues tend to get farther apart. So in this case, the only thing that you might have thought could have happened, perhaps, is that it could have been, let's say, like this. Maybe they would have crossed and done something like that. And basically that never happens. They always get repelled from each other. Eigenvalues that start off a little bit different just move away from each other and sort of never cross like that. Okay, questions about that? All right. So let's move on to a new topic. This is a different approximation method called the variational method. Actually, we're going to return to the perturbation theory to do one more great example, which is the helium atom. But I want to actually do the variational method first. And then when we do the helium atom, we're going to do the helium atom two different ways. We're going to do it with perturbation theory, and we're going to do it with the variational method that I'm about to show you. And we'll see which one does better. Okay, and so this is also known as the Rayleigh-Ritz method, or the Rayleigh-Ritz variational principle. Okay, and so let's start with the key idea, which we will then prove. So the key idea here is that, let's just say for you have any state whatsoever, you get to pick it, and we'll just call it a generic state psi. It's not necessarily an eigenstate of anything. Then it's true that the exact ground state energy is less than or equal to the expectation value of the Hamiltonian in that state that you chose randomly. Okay, and I'm going to do this in a way, we're not going to assume that psi is normalized. We're going to assume that psi may not have unit norm. And that's really just a practical thing that sometimes we're going to get lazy and we don't want to normalize the state. So, okay, so in the end, we don't have to normalize the state as long as we remember in the end, when we compute this, we're going to have to divide by the norm. Okay, and so E0 here is the exact, by definition, the exact ground state energy. All right, now that's supposed to be true, and we're gonna prove it in just a minute or a few minutes. But that's supposed to be true for any psi that you get to pick. But now what we're going to try to do is use a little bit of cleverness in choosing which psi we pick. So we're going to choose our state psi to be close. I'll put that in parentheses because in practice, we may not know how close to the true eigenstate, the true ground state energy, or the true ground state, I should say, which we can call the ket, which we're just labeling it by its eigenvalue, E0. So if you choose it close, then it ought to be true. And again, we're going to prove this, that the true ground state energy should be pretty close to this expectation value of the Hamiltonian divided by the norm of the state. Okay, so there are two aspects of this. One is that you get a bound that says the ground state energy has to be lower than this thing. And then it's that if we make a good guess somehow, then it should be close to equal, not just a bound. All right, so this method is a non-perturbative method. That's the great thing about it. You don't have to worry about things converging or not, because we're not going to do an expansion this time. That's what we mean when we say it's a non-perturbative method. Okay, and that means we don't need an exact solution for anything. In perturbation theory, there has to be some problem for which you know the exact solution, but here that's not the case. So there's no unperturbed H0 in this method. You just treat the whole Hamiltonian all at once. On the other hand, you don't get anything for free, so you do want to make a good guess for your state psi. So you do want a good guess for psi. And what's a good guess? So for example, you probably don't want your guess to have lots of wiggles in it in the wave function. Okay, so the wave function, I'll write this in the language of a 3D problem. So if we write down the wave function like that, this should have as few wiggles as possible. Except sometimes you have to have some wiggles in it because maybe your potential has wiggles, and if your potential has wiggles in it, then the state will tend to have wiggles in it too. So why is that? That's just because wiggles means non-zero derivatives, and non-zero derivatives go into the kinetic term. And so if you have non-zero derivatives in the kinetic term, it's going to make the kinetic term larger. And so this is really to minimize the kinetic term. Since we're looking for the ground state, we want the energy to be as small as possible. And the kinetic term, meaning the p squared over 2m term in the Hamiltonian, doesn't like that if you have lots of wiggles. Okay, and then counteracting that, you want the wave function magnitude to be smaller where the potential is larger. So in places where the potential is large, then you get more energy, you get a larger energy where that is true, and so your particle wants to avoid being near there. So those are two sort of qualitative things that you can use to help you make a good guess. And so you can do that. And the other thing you can do to make a good guess is not just make one guess. You can make lots of guesses at the same time. So that means what you can do is you choose your guess as a function of a parameter or parameters. So here A equals some parameters, just some variables that you are introducing as part of your guess. I've written it as one, which I've called A, but in general, there will be more than one of them. Okay, and so then the idea is to apply the variational principle. What you do is you compute the E of A for your guess, which is defined to be this. It's defined to be the thing that we're claiming is bounded. And so what we're really doing is we're doing lots of guesses all at the same time. And now we're going to choose the best guess by minimizing this. So minimize it, which means that what we're going to do is we're going to look for an extremum, which is where its derivative equals 0. And many times this is just automatic, it will turn out. But you want the second derivative of E with respect to your parameter to be positive. Okay, so those two things will tell you that you're near a minimum. And so if you solve those, then you will find that the minimum is something we can call a minimum. And then our best guess for the energy of the ground state, E ground state, is just the function E evaluated at A equals A min. And our best guess for the wave function of the ground state, or the ket of the ground state, is just psi of A min. Okay, so that's basically what I've done there is told you what to do, but now let me prove that it actually works, which is a sort of a two-line proof. And of course, it's then we'll do lots of examples. Because examples are always better than writing down equations. So here's the proof that it works. Let's just compute psi h psi for any old state. And the way we're going to do that is by using completeness, because that's pretty much what we always do when we don't know what else to do. And so we're going to include a complete set of energy eigenstates. Okay, the Hamiltonian is an observable, so we know that we can do this by definition. Okay, and now the point is that the Hamiltonian acting on our E sub n is equal to E sub n. So we rewrite this by just pulling out that number. Okay, and now this is greater than or equal to, that should be a greater than or equal to, E0, because E0 is less than En by definition of the same thing, but now I've pulled out the En and I've called it E0. Okay, and now I can once again use completeness because all of this stuff, when I sum over n, is just the identity operator. So this is equal to E0 psi psi. And now I just divide by psi psi and I got what I claimed, that the ground state energy is less than or equal to the expectation value of the Hamiltonian divided by the norm of the state for any state psi. Okay, so that's the end of the proof. Now, that's the proof that it works, but there's one more thing we can do, and that's we can estimate not only does it work, but how well does it work? And the answer is it turns out to work very well, perhaps better than we might naively have thought. And so to see that, let's suppose that we made a reasonable but not perfect guess. So suppose we guess that psi was actually the ground state, plus we made some not quite perfect guess. So there's going to be some sum over all the other eigenstates of the energy multiplied by some numbers delta sub n, and we hope these are small. But since we're just guessing, we can't be sure that they're small. Okay, but if we made a perfect guess, the delta n's would all be 0. Okay, then we can compute psi h psi, and that's just E0 plus sum over n greater than 0 of E sub n magnitude of delta n squared. Okay, that's just putting the Hamiltonian in between the bra and ket for the state and computing it. And then for the norm, I assume that my energy eigenstates are norm 1 or normalized. So that looks like this. Okay, it's just 1 plus the norms of the delta n squareds. And so now if we compute the thing that is supposed to give us our estimate of the energy, like so, that's equal to, we just write what we got. So there's 1 plus some n greater than 0, delta n squared. Okay, plus some n greater than 0, En minus E0 times delta n squared. So all I've done is I've rewritten this thing, but I've separated out the part with E0 and the part with the delta n, the En minus E zeros. Okay, and then in the denominator, we have just the same thing as is multiplying the E0 in the numerator. Okay, and so I can simplify this and write it as E0 from this part plus a sum n greater than 0 En minus E0 times delta n squared, all divided by 1 plus, so it's the same denominator. Okay, so now here's the whole point of this, is that this is the correct answer right here, and this is the correction to it that we're getting because we didn't make a perfect guess, and so that's our error, and the error is not proportional to the deltas, it's proportional to the deltas squared. So what does that mean? That means if we made a guess that had sort of 10% errors in it, then our error in the energy would only be 1%, and so on. So the energy that we get is much better than the guess. Okay, and another way of saying that is the variational principle is happy to forgive you if you don't make a perfect guess. In fact, you can make a pretty mediocre guess. Again, you can be off by 10% in your guess for what the wave, for what the state was, and it's still happy to give you back an answer that's good to 1%-ish. Okay, so that's the idea. And next time we will apply this and see how well it works in various examples, ending up with the classic example for this, which is the helium atom. All right, that's it for today. Are there any questions on today's lecture?
I've got some questions from the notes.
Okay.
Right. So yeah, in the when we were still in the degenerate part, basically had like the unperturbed state plus lambda times the first correction plus lambda squared times the second correction, and so forth.
Yeah.
Then I noticed in that example you had in your notes, you didn't put lambda in. So like later on, like I was wondering whether when and where we do include the lambda, and when and where do we just ignore it.
Right. So we're not really ignoring it. We're setting it equal to 1. And the reason we're setting it equal to 1 is just to make things simpler. So the original reason for keeping lambda is just that it's telling us for any term that we write down, it's telling us what order in perturbation theory we're working in. If it's got a lambda in it, then it's first order. If it's lambda squared, it's second order. If it's lambda cubed, it's third order. But that's really the only reason lambda's there, is just to tell us that. And so then once we've derived a formula that, let's say, is at second order in perturbation theory, then we don't care about doing this counting of orders anymore. And so we can just set lambda equal to 1 and everywhere in everything we've done. And so that's what we do sometimes.
So basically you're saying it doesn't interfere in the calculations. That's just like a symbol we put there, like a label, so we'll know what order of the correction it is, correct?
That's exactly right. Yep.
Oh, thank you. Another question is in the notes, and here's what's interesting. I didn't see you do this in class, but I saw it in your notes, and I saw it a few places.